In 2022, we had a deferred exam option that normally is not offered. Uh, Normally what happens is if you miss the final exam, you're given an opportunity to write with the summer course of MIE 100 and you take that final exam. However, because of COVID, there was a decision to go forward with a deferred exam. So in response to COVID, a special exam, similar goals to the final, and a smaller sort of population that took it. So it was about 30 students. Same organization as the other exams, but just starting here, I have a 14,000 kilogram truck that supports a 9,000 kilogram vehicle on a 5-degree ramp that is built onto the truck. Neglect all friction and treat the vehicle and trucks as particles. So you can tell right away that this is going to be a problem that is particle kinematics and kinetics. What is the change in potential energy for the system of the vehicle and the truck when the vehicle is rolled down 9 meters down the ramp just before hitting the stop at B, 3 marks? What is the velocity V of the truck when the vehicle has rolled down 9 meters down the ramp just before hitting the stop at B? So one thing you got to realize is that this is a relative velocity problem. So you have a velocity that I'm going to kind of term S dot, which is associated with this vehicle here. And you have the velocity of the truck here. So that goes with V. This is moving with S dot. System is conservative, and you first analyze the flat car, and you sort of say, well, it starts at 0 velocity, it ends with a final velocity. The mass of the truck is given as 14,000 kilograms, and delta VG is equal to 0. To analyze the vehicle, you have to recognize that, much like you do later in the course, vehicle velocity is going to be velocity of the truck plus velocity of the vehicle relative to the truck. So you add the terms in, 1/2 9,000 kilograms, S dot cos 5 degrees minus V, because that's the X component, squared, plus S dot sine 5 degrees squared, and minus 0, because it starts at a 0 velocity also. Change in height is going to be the change from the top to the bottom, and you can calculate that. So this both deals with the velocity of vehicle right here, which is with respect to the ground. This is velocity of vehicle X, velocity of vehicle Y. No surprise here, because the truck doesn't move horizontally or vertically, it doesn't have a Y component for the truck. Putting all the terms in and simplifying, you end up with this equation right here. So for the system, sum of forces in X is equal to 0, so change in linear momentum is equal to 0. Substitute in all the terms, you got to do momentum. Substitute everything into equations, 2 unknowns. You have to find S dot in terms of V, and that's here. And you end up with V of 3.81 meters per second. This is a problem. It's a challenging problem, and it's one that probably is one of the more challenging parts of particle kinematics and kinetics, in the sense that it has a relative velocity, and that often proves more challenging for students than other types of problems. Particle kinematics and kinetics with a focus on work energy, and here we're covering chapters 2 to 4 of the Merriam and Craig book. Question 2, a uniform disk, little r equals 1 meter, and that's little r right here. There you go. On a circular surface, big R equals 2 meters. So that's big R right here. Rolls without slipping. In the position shown in A and B, the disk has an angular velocity of 4 rads per second and angular acceleration of 2 rads per second. You're given the directions in the figure. Determine at the bottom position shown in figure A, the acceleration of point C on the disk in contact with the surface. And you do the same thing with point B. You'll notice here that it sort of is inwardly curved and it's outwardly curved here. And that's going to be the important thing in terms of determining that acceleration. So we're interested only in the acceleration of point C, which is acceleration of O plus acceleration of C relative to O. And if we do that for the first half, remember that that is on the inner side, and the curvature is like this, and point O is over here, C is over here. C is a point of no slip. And because of that, the acceleration tangential of O is r alpha in the I direction, but at the acceleration of C relative to O is minus r alpha. So these two terms go away. For the normal acceleration, the radius of curvature is r minus r, and you end up with this term at the bottom of 32 meters per second in the j direction. Same thing happens over here, but the difference is that now you have a radius of curvature that goes all the way down. It's at the outside. You still have the same thing. Tangential acceleration at O is r alpha, and it's minus r alpha here. And so the tangential component at a point of no slip, and that's a definition. If you look at those videos, again, you'll see that. And the only difference here is the r plus little r. In this case, r omega squared, and you end up with r omega squared 1 plus r over little r over big R, j 10.67 meters per second. And that's the difference between acceleration of C is 32 meters per second in this, on the inside curvature, and it's 10.7 meters per second squared on the outside curvature. The next problem is a uniform bar that has a mass m equals 15 kilograms, length L equals 2.6 meters, released from rest on a frictionless surface in the position shown. Frictionless surface is angled with 30 degrees with respect to the horizontal. Draw a free body diagram. Find the initial acceleration of point A when the bar is first released. Express your answer in the coordinate system shown in the diagram, 6 marks. Okay. I actually did a video on bars hitting ground and at various angles and all sorts of things. And this is a common problem in dynamics, and one that a lot of people want more to happen than it is. So you look at this diagram and you start to overthink it. And that's one of the dangers in MIU 100 is that you overthink a problem. So, but all we have here is a ramp at 30 degrees. We have the axes given to us, and we have a gravitational acceleration, which is acting down. So the first part, asks us for a free body diagram. The only forces acting here are the normal force, which is acting at 60 degrees to the horizontal, and weight, which is acting downward. So we have that. So now you have the sum of forces in x and y. You can say that the sum of forces normal in the x direction is going to be Fn cos 60 because it's acting in the negative sense. You have a negative value there. And that's magx. And that's acting in that direction. And for Fny, it's acting upwards and it's positive. Weight is acting downwards, and you have magy. You expect this also to only have a component from force normal x, and that will cause a rotation that's clockwise, Fn cos 60 L over 2. That is equal to 1/12 ml squared alpha, and you recognize, or you need to know, that you are looking at a problem where alpha is, moment of inertia is 1/12 ml squared for a long slender rod. This is something that should be on your crib sheet and you recognize right away. You can then break it down into acceleration AA. The object is, the rod is expected to sort of slide down the ramp, and so cos 30 and sine 30 in the y and x directions, and you have this sort of solved through. Okay, so that's everything there, and you just recognize L over 2 alpha I for that rotation. And acceleration of A here is just referencing the magnitude of acceleration of A. Substitute in the terms, calculate everything through, and you end up with these two equations here. Substitute the numerical values back in. You have an acceleration A term and an alpha term and a normal force. You have an acceleration term and a normal force in the second equation. And finally, you have a normal force in terms of alpha. So you have three equations, three unknowns, substitute in, and you can solve through for alpha, which is minus 5.61 rads per second squared, and acceleration A, which is equal to 11.2 meters per second squared. And acceleration A direction with the directional components minus 9.71 I plus or minus 5.6 J meters per second squared. Rigid body kinematics and kinetics. Kinetics and kinematics, excuse me, chapter 5. Finally, or not finally, you have a slender rod that it's coming down. The tricky bit here may be over here where you have a two springs, and because you have the two springs, oops, there we go, you got to consider springs in parallel. So the springs are attached, two closely spaced parallel springs. K1 is 12 kilonewtons per meter, K2 equals 20 kilonewtons per meter, and they're compressed by 2.8 centimeters. The rod is in a horizontal position. Determine the angular velocity of the rod when it reaches its vertical position. So when it is going to look like this, and determine the reaction at point O, which is defined as the pinpoint here, where in vertical when it's in that vertical position. You're given the weight. So again, one of those funny problems where we give you weight. G mass is 5 kilos. Length from G to O is 0.2 meters, bring all of that terms. And you know it's a work energy problem, and you can start with position 1. And if you do that, you have gravity, and we've defined here and as a datum right there. So VG1 is 0. Springs are initially compressed, and they have 4.7 and 7.8 joules respectively. So total initial potential is 12.5 joules. T1 is equal to 0 because it starts from rest. You release it, and it swings into position. At that point, it has a gravitational potential. All of the spring potential has gone because there's nothing else left. And you have T2, which is going to be a combination of the translational and rotational velocity. If you do it at G, if you do it at point O, you'd have only rotational. So T2 is equal to 1/2 mv2 squared, 1/2 Ig omega 2 squared. Ig, for a long slender rod, we didn't give it to you, but you should know this, 1/12 ml squared, put the terms in, 0.27 kilogram meter squared. V2 equals R omega 2 and 0.2 meters omega 2. T2 is 0.233 omega 2 squared. T1 plus V1 equals T2 plus V2, conservation of energy. Substitute in terms, and you only have one unknown, and that is omega 2. And omega 2 is equal to 3.423 rads per second. Next, you're asked for the reaction force at the pinpoint. You know the acceleration normal, you know the acceleration tangential. Acceleration normal is r omega squared, 2.3 meters per second squared. Acceleration tangential is equal to 0 because alpha is equal to 0. Reaction force at x then at that point is 0. Reaction force at y is equal to 37.3 newtons. Rigid body kinematics, kinetics, and work energy, so 5, 6a, and 6b, and a little bit on springs in parallel. Finally, it's the vibration problem. Again, you should be expecting these. The mass of a spool is given as 20 kilograms, radius is 0.3 meters, and you're given in this problem, because we don't expect you to know cylinders or spools, an Ig of 1/2 mr squared. The spring constant is 60 newtons per meter, and the damping constant is 24 newton seconds per meter. Draw the free body diagram. What is the equation of motion for the system? What is the position at t equals 1.5 seconds? The disk is released from rest at its static equilibrium position when t equals 0. So it's at static equilibrium. Mass of the spool is given as 20 kilograms. R is equal to 0.3 meters. K is 60 newtons per meter again. So in looking at this, you need to recognize, first of all, that you have an instantaneous center, and that's the point where the cord comes in contact. It's over here. You have the weight, which is acting downwards. You have spring force or spring displacement, and you have the dashpot displacement. And so each of these are going to displace x double or twice x dot and 3x dot from this point over here. This is going to end up being a moment problem. If you look at the static equilibrium case, it's going to be mg minus kxst, which equals 0, and the static equilibrium position is mg over 4k, the spring constant. Dashpot doesn't play a role in the static case because it doesn't move, so there's no velocity associated with it. So you have tension acting upwards, you have spring force acting upwards, you have dashpot acting upwards, and you have weight acting downward. Substitute in terms, x, remember that it is defined a little bit differently in here. It still follows the right-hand rule, which is always a good thing to do. Its mg is down as positive, minus t, which is acting upwards, minus twice kx, minus 3c x dot equals mx double dot. For the other terms, you have everything for moments about g. G is the center of this disk or spool. And it's minus RT plus twice kx times r plus twice r 3c x dot equals, and in this case it's a spool and you're given minus mr squared over 2 theta double dot. Theta double dot you can get from sort of the standard trig relationships or geometric relationships in MIU 100, and that's theta double dot is minus x double dot over r. And it's minus because it's going downward, and downward is positive in this case, and clockwise is negative. So theta double dot in this case, as it rolls down, is going to be a negative. So now that we have the equation of motion, I can substitute in terms, get everything, combine them up, and I end up with this. And this term here is my equation of motion. And as you're kind of aware by now, you know that this term is going to be my damp term. This is my spring term, and this is my acceleration term over here. So x double dot 6c over m, x dot 8k over 3m x is what I'm working with. I can calculate the natural frequency using this term right here. So 8k over 3m, and I get 2.83 rads per second. Now, if I substitute that back in, 3c over m omega n, I end what? 0.273. And now, beginning of the slide, I didn't have this animated properly clearly, so it's overdamped. Solution is the standard form within Merriam and Craig for overdamped vibration. It's going to start to do this as it goes down, and as it does that, I end up with an equation that looks lambda 1 minus 1.31 or 729, and lambda 2 minus 5.8721. Time equals 0. X0 is the static position, which is that term I calculated on the previous slide, and it's 0.18782 meters. X dot at 0 is 0, and my equation ends up being 1.0695 e to the minus 1.3729 t minus 0.252 e to the minus 5.872 or 8271 t. I don't like doing this. And I end up with a final result at 1.5 seconds of 3.4 or 1.1364 meters. So it's similar topics to past final exam. It's a focus on the second half of the course with material from the first half of the course.